This is MSE 1593 Fundamentals of Material Science class number 2. And in this class, we are going to continue talking about um, the fundamentals of material science. In the last class, we covered the different types of bonds like, ionic, covalent, and metallic. And then we talked about crystal structures and amorphous structures very briefly. We talked about different types of lattices, etc. We also talked about directions, and we are going to talk about planes and the, the information about different types of planes and what connection they have with material properties and so on. And I would like to know if you have any questions. Please do send them to us if you have any questions. So in this class, we are going to continue talking about directions and planes, and then we will talk about crystal structure determination methods. Um, then we will start talking about the different types of point defects, and then we will go and start discussing the thermodynamics of defects. Okay, so for those of you who remember your fundamentals from material science, this may be a refresher, and I hope that is the case. Okay, so talking about planes, we can represent the planes. The shaded area in this diagram is a plane. So this is the Cartesian coordinates of a system uh, for representing a lattice, a unit cell, and the directions and planes. So you can see that the x direction would be is termed as B here. This is termed as A, and this one is termed as C. Those are the three directions, or you can also call them X, Y, Z. It doesn't really matter. So only thing is that you have to be worried about the origin. So this shaded area where it intersects with the different planes, different directions, is called a plane, and how you represent them is given by what are called Miller indices, and it is given in round brackets. And those indices they have to be integers, and they are given by represent them in a generic fashion by UVW, and this is meant to specify the orientation of a plane and not the vectors themselves. And what is to note is that these are the reciprocals of the intercepts of the plane, and those numbers are whole integers. So if you have a fraction, you have to multiply them to get whole numbers. And again, just like in the case of directions, there are two conventions to note. If the plane intersects on the negative side, then that number alone is called H bar, which represents the minus part of the intercept. No intercept, or if it intercepts at infinity, means the inverse is equal to 0. So that's one of the reasons why you have to take the inverse. So many times this plane may not even intersect with a plane with a direction, so which means that the intercept is 0, and the inverse of the intercept is 0, and the intercept itself is considered to be infinity. For example, if it is plane 110, means the intercepts are 1, 1 and infinity. 120 means the intercepts are 1, 1 half and infinity. 1, 1, 1 bar means the intercepts are 1, 1 and minus 1. So if you know the intercepts, you can draw that plane. And why is a plane important to know? I mean, why is this information important? It is important because many times, for example, if you are deforming a particular material like copper, okay, copper is face-centered cubic, so which means that there are certain planes and directions that are much easier to deform. So these planes are supposed to help you to characterize the material. Suppose you see something and if you can characterize it as a particular plane, and if you see a lot of them, then you know that this is a one particular type of material. For example, the close packed direction in face-centered cubic would be something, and the dislocations or the deformation strands or striations are supposed to be seen mostly in that particular direction or that particular plane. So if you see that, then you know that it is this particular material. So, what is a useful fact? Useful fact is, and this is mainly for cubic systems. So, the direction given by the three integers of the direction HKL is normal to the plane, simple brackets HKL. Okay, so you can calculate the angle between the direction and the plane, and it will turn out to be equal to 90 degrees. So you can use that information to characterize the particular material system. The other useful fact is to check if a direction is contained in a plane or not. So for that you have to take the dot product of the two vector systems. For example, is the direction 1 1 1 bar contained in the plane 1 2 3. So this is the direction 1 1 1 bar and this is the plane 1 2 3. So can we figure out if that is in that direction or not? So you know that in cubic systems the normal to the plane has the same value as the direction. So if the normal to the plane and the direction are at 90 degrees to each other, then the direction is in the plane. Okay, and you calculate that by using the dot product, and dot product for 1 2 3 and 1 1 1 bar are equal to 1 times 1 plus 2 times 1 plus 3 times minus 1 equal to, and divided by the square of the numbers. 1 squared plus 2 squared plus 3 squared is equal to 14, and 111, the square of those, the summation of the square of those is equal to 3. So root 14 times root 3. So if you take this, it is equal to 0 because the numerator is equal to 0, which means the value is theta cos theta, or theta is equal to 90 degrees. So which means that the two vectors are at 90 degrees to each other, and you know that HKL okay, square HKL is normal to the plane HKL. So using that factor, you can calculate the vector dot product to find out that this particular plane and this particular direction are contained in each other, or the direction is contained in that plane. Okay, so in coordinate geometry terms, this is given by the relationship vector A dot product vector B is equal to the summation of AB times cos theta. You can also do the same thing to see what is the line of intersection of two planes. So 110 and 111. If you know that, and if you know that this is direction UVW, then you get that by taking the cross product of the normal of the planes. Okay, so if you do that, you should be able to get that. I'm not going to solve this for you. I want you to just go and look it up yourself. And the other thing I want to point out is, I know that you would have covered this a long time ago, but I just want to refresh your memory. This type of a bracket, UVW contained within this kind of a bracket, is the family of all equivalent UVW directions. And squiggly bracket UVW is the family of all equivalent simple bracket UVW planes. So if it is, for example, if it is 100 plane, the family of all planes is 100, 010, 001, 1 bar, 00, 0, 1 bar, 0, and 0, 1 bar. So they are all equivalent and related by the symmetry operation. I think we talked a little bit about that in the last class. So symmetry operations are, so if you move it by a certain angle, they will still be equivalent and related by the symmetry. I mean, it's just that the orientation at which you look at that particular direction or plane is different, that's all. But they remain the same. So if you change the orientation of your coordinate axis, they will still remain the same. For example, 100 might be 001 in another direction, because they can be interchanged by a 90-degree rotation. So how do you correlate all this? Why is this all important? Especially when you are wanting to calculate the crystal structure of an unknown material. So the way in which you do that is, the standard method is X-ray diffraction. And it may be known to some of you already. So I want you to take a look at the handout that that we have posted in D2L. And as I said to you before, the crystal structure is a combination of a point lattice and the basis group. So the two major aspects to diffraction is the Bragg's law, which will give you the peak positions, and the structure factor equation, which is correlated to the actual intensities of the X-ray beams. So if you assume that, or if you imagine that the crystal is a set of regular planes, you expose the crystal to an X-ray beam of a specific intensity, and you rotate that beam through a certain angle theta, and when that happens, you get a spectrum of this sort. This is an example spectrum, and these peaks where you get these sharp intensities are going to be dependent on particular atomic planes. And then you can take this information and work out the structure. For that, please take a look at the handout that we have posted. So what is Bragg's law? Bragg's law is states that if you have an incident beam at a specific wavelength lambda, they will get a reinforcement of the beams at a particular angle theta, and it is given by this relationship n lambda is equal to 2d sine theta, where the d is controlled by the d-spacing of that particular atomic plane, and n can be um, vary from 1, 2, 3, and so on. So that's the order of reflection. So you might find, I mean, you will definitely find the first order of reflection, you will find the second order of reflection, and so on. But the more these things, the intensity might not be as strong as the first and second order of reflection. So for this, you have to do what is called a scattering analysis. And for this, you also assume that each of the atom will act as a scattering center. And we can measure the scattering power by doing a scattering analysis. For that, you have to know what is called the structure factor, FHKL, which is a structure factor. You might be learning more about this in the diffraction class. And so the intensity is proportional to the square of the structure factor, and which is equal to FHKL times F prime, small f prime, HKL. So that is the intensity that will cause a reflection from one particular atomic plane. And this is also where the structure factor is defined as equal to LHKL times BHKL. LHKL will depend upon the lattice type, and the BHKL will depend upon the number of atoms in the basis or crystal structure. I know that I'm going pretty fast over here, but you know, these are all fundamentals of material structure determination. So I will let you read the book and understand about it more in detail. For example, if you have pure copper, it is an FCC lattice. There is one copper atom on each lattice point, and if you have the atomic plane HKL, that is a combination of odd and even, then the structure factor is equal to 0, which means that the intensity of that intensity will, I mean, you will not have any peaks related to a combination of odd and even planes. But if you have HKL that is all odd or all even, then you are going to get reinforcement. So which means that you will have a very sharp peak for HKL that is all odd or all even. The same way, if you look at silicon, you have two interpenetrating FCC lattices. It's called the DCC structure, and you have 2 atoms per point. And if it is FHKL, that is a combination of odd and even, you are not going to have any reflections at all. But if you have HKL that is all odd or all even, except in cases where HKL is even multiple of 2, then it is equal to 8 FSI for all odd or all even. So you will have specific intense peaks related to those HKL values. So where it is going to be is also given in handbook, so you will be able to know what are those peaks, and from that you can determine what material it is or what material combination it is. So now let us go to the discussion about point defects. So there are 2 types of, and these are in sections 3.1 and 3.2. This is from chapter 3. So if you look at that, you will see that there are 2 classes of defects. One is where you have chemically related defects. You have 2 chemically different species, A and B. And the next one is structural defects, where you have the same pure material. So the chemically related species are where you have what is called a solid solution. So there are 2 types of solid solutions. One is a substitutional solid solution. The other one is an interstitial solid solution. In the case of structural, you can have what is called self-interstitials, where you have the same atomic species in between positions where it is not supposed to be. And the most common one is where you have a vacancy or multiple vacancies in the crystal lattice. So these are the sizes of defects that you will find in crystal structures. If you have point defects, then the size is one single atom, the size of one single atom, 10 to the power minus 12 centimeters. Or if you have an atomic point defect, if you have single atoms that are missing from the structure, or if you have an extra atom that is in position where it is not supposed to be, then the size is of that of a single atom. So that one is of the order of 1 angstrom. Then you can also have line defects where you have for example, if you have a grain boundary, that would be a line defect. Or you could have say for example, if you have a surface, that would be a line defect also. You could also have a bulk defect where you might have many groups of atoms that are missing, or there could be some kind of a volume defect. So that would be a bulk defect, and those sizes are much bigger than a single atom and things like that. So here is a schematic of the various types of defects. You can have substitutional impurity atom, or you can have interstitial impurity atom where it is smaller than the substitutional impurity atom, or you can have single atoms that are missing, or the same atom could diffuse into a point where there is not supposed to be, so that is a self-interstitial atom, and so on. So here is a schematic of chemical defects. Due to impurities in a host, and again, as I mentioned to you, they can be either substitutional or interstitial. In structural defects, the vacancies are the most important. Self-interstitials are important only from the point of view that they are very rare, and they are formed most often when you are exposed to very strong energies, like in the case of radiation energy, where they can push those atoms into interstitial positions by the radiation energy. So, if you have to learn about substitutional solid solutions, you have to know what are the conditions necessary for those solid solutions to form. And there are empirical rules, and they were originally developed by a professor from Cambridge. His name was Hume Rothery, and they are listed after him. And one thing to note is that there are very few materials that have complete solid solubility in each other. So the rules for the best substitutional solid solubility are, first of all, they have to have the same lattice structure. And second of all, there should be very little difference in atomic size between the two types of atoms. The third important requirement is that they should have the same valency. If not, they will form an intermetallic or compound. And the fourth one, that is not as important as the first two, that is the difference in electronegativity between the two different atomic species. They cannot be more than 0.4. For interstitial solid solubility, I'm sorry, that should not have the same lattice. They will not be the same lattice structure. But if they are, then it could be good. But I don't think that that is correct most often. But the most important thing is that the solute atom should have a radius no larger than about 60% of the radius of the solvent atoms. So there are two types of atoms. One is the solute atom, the other one is the solvent atom. The solute atom is the species that is in the lower percentage values compared to the larger volume atoms. Okay. So for interstitial solid solubility, then the solute atoms that are in the interim areas of the structure, they should not have a radius larger than 59% of the radius of the solvent atoms. And that's because if you have too much, then you are going to be introducing a lot of strains in the system, which is not going to be energetically favorable. They should have the same valency and they should show a wide range of composition. So one thing to note is that there are very few elements that would follow this. Others will show limits on solubility in each other. So it's not that they can show 100% solubility in each other, but they will show some small amount of solubility. How do you overcome the limits on solubility? By increasing the temperature. If you increase the temperature, more of it will dissolve in the other material. For example, if you have sugar, okay, you are trying to dissolve it in water. If you add a lot of sugar into water, there is going to be a limit to the amount of sugar that you can dissolve. So how do you overcome that? You heat up the water. By heating up the water, more of the sugar will go into solution into the water. Similarly, if you heat up the solvent atoms, then they can take more of the solute atoms into solid solution through the addition of the extra energy. And these are given by phase diagrams. So most of you must have seen, phase diagrams related to gases or liquids and so on. But you should note that, you may have done that when you did your undergraduate material science class. So you must have done some of it there. But what you need to know is that there are very few elements that are completely soluble in each other. Something that is a good substitutional solid solution is copper nickel. They are soluble in each other in all proportions, but others all have limitations to the amount of solute atoms that can be added to the solvent atoms. So there are examples of good interstitial solid solutions. For example, you have iron copper, which is the basis for all steel phase diagrams, or you have iron and nitrogen, which would contribute a variety of good engineering applications. So the structural defects as I said to you, there are two types, and the major one is a vacancy, and the amount of vacancies, the volume of vacancies can actually go up when you increase the temperature as a function of the diffusion coefficient. So if it is under thermal equilibrium, it will contribute to a specific amount of vacancy concentration, control self-diffusion, etc. One thing to note is that if you have self-interstitials, then they will distort the lattice. And the vacancies also distort the lattice. They will kind of collapse the lattice, but it is not going to be as difficult as self-interstitials. So structural defects tend to disturb the energy of the crystal or increase the internal energy, and they are not always energetically favorable. They are energetically unfavorable. But in the case of chemical defects, it is not very clear, but most of the time, those chemical defects actually are more energetically favorable than structural defects. So that finishes up the discussion about defects. And please, if you look at the homework sets, you will see problems related to all these, and you should be able to at least have an understanding of the problems related to these questions. I have posted a handout related to Principles of Chemical Equilibrium by Denbigh. Please go take a look at that, and you should find more information about it. So, for understanding thermodynamics, you need to know what is a state variable and what is a regular variable. State variable is typical variable. You have internal energy, you have pressure, you have temperature, volume, etc. So those are all state variables which you can correlate to the current state of the system. For example, if you have color of hair, that is a state variable. If you have number of hair or fingers, that is a state variable. But the time it took for somebody to drive to class, that is not a state variable. So, in solid systems, for example, two variables that are important are elastic strain and plastic strain. Elastic strain is a state variable, whereas plastic strain, it is not. Because plastic strain will depend upon the condition, the application of prior strain and releasing it and so on. You do not know where in the tensile stress strain curve you are. So you cannot really, it will be very similar to driving time to class. Okay, so the same way, your plastic strain that you have introduced is really not constant. So because of that, plastic strain is not a state variable, but elastic strain is. So, for example, if you have the amount of work that has been done by this system, you have mass W or weight W, and you move that by a certain distance dx. So the work done dW is equal to F dx. F is the load and dx is the distance by which it has been moved. You can also have pressure minus work done is equal to the expansion of the system, PdV. If you are loading up a material in tension by a certain strain d epsilon and you are applying a certain stress sigma, then it is equal to dW, the work done, is equal to sigma delta epsilon. If you have electric field, you can define it in the same manner. The other things that you want to know is the other way of transferring energy is through heat. So if you can transfer energy through either work or by heat. So work means it's termed as dW in heat is termed as dq. So you can have different ways of defining these energy transfer terms. Okay. So in thermodynamics, we always talk about the first law of thermodynamics. What is the first law of thermodynamics? In this case, especially for crystal structures, it relates to the energy content of the system expressed by the internal energy of the system. So the same way, I mean, for any system, you have a combination of potential energy and kinetic energy. And I mean, your standard one is that you neither create nor destroy energy, right? So because it is always constant. Okay, so the internal energy is a combination of potential energy and kinetic energy. For any crystal system, you can define the potential energy and you can define the kinetic energy. So what is the potential energy? Potential energy is due to the state of the presence of crystals or atoms. And the kinetic energy of the system is dependent on the amount of vibration of those atoms. For example, if you have heated it up, then it's got a certain amount of potential energy, but its kinetic energy will increase. So in the same manner, potential energy should decrease because so that it will maintain the total energy of the system. So the potential energy is due to the primary bonds where the atoms are separated by a finite distance, and the kinetic energy is due to the vibration of the atoms, little chunks of mass vibration, lots of normal modes of vibration. So that will all contribute to the kinetic energy of the system, and that gives you the total energy of the system. So if you assume that the system is of fixed mass, so if you transfer heat to the system, it is considered to be positive, and the work done by the system is considered to be negative. So you have certain input dq and a certain output dw. So both these are positive, but the amount of energy that is remaining in the system is equal to dq minus dw. And that is the amount of energy that is remaining in the crystal structure. So that is the first law of conservation of energy. So that should remain the same. Or it is a combination of potential energy plus kinetic energy. The other thing to note is that there are reversible versus irreversible processes. So your state of equilibrium means your system is stationary or unchanged with time, and this leads to the idea of reversible processes. And it is a quasi-static progression of equilibrium states, and it has no natural direction in time. And an irreversible process is a progression of non-equilibrium states and is not quasi-static. And they do have a natural direction as time passes. Let me explain what that really means. For example, if you have a system, a gas, in a container, okay, with very smooth walls. So you have a piston and you put a tiny weight on top of that, or tiny small weight, and the system will move very slowly to its next state quasi-statically. So for all intents and purposes, it is always in equilibrium because it changes very, very slowly. What you need to know is that it is a reversible process because you can always add or remove the weight. And the system has no natural direction. So you are literally talking about quasi-static compression of gas. But suppose you have two chambers, one where you have gas and the other one you have vacuum. So if you suddenly open the valve, then it is a reversible process. The gas is going to escape into the vacuum area, and there is no way for that gas to escape back into the container. So you have lost the amount of volume of gas and there is no way for you to recover back. So there is a natural direction for this system. Eventually the system will settle down, but while it happens, it is not in equilibrium. So the basic issue for this is that, is there an equilibrium state for some of the conditions that you have defined, and whether there is a natural direction of the process. We are not interested in the rate right now, but we want to know if there is a natural direction of the process. So it will be useful to know that it happens, but not practical to know how long it is going to take. So there are three types of constraints that you can have. The first one is whether the system is isolated. It is out of touch with everything. It does not exchange any mass or energy with the environment. That would be the first type of system. The other one is the closed system. There is no mass exchange. This is more typical. You can have energy exchange, but there is no mass exchange. And the third one, which is the most common one, it has both mass and energy exchange, like solids. You can in general ignore the exchange of mass. So you can have stable versus unstable equilibrium. So suppose you have a trough and you have an atom or electron and you are pushing it up by a certain distance dr. Because of the slope, if you leave it, it is going to come back to normal. So it is a stable equilibrium and you really do not have any natural direction in which it will go up or down or anything like that. It is just that this is the most natural state for this particular system. It will always try to return to its initial equilibrium state for small displacements. You cannot push it out so much that it goes out of the trough. You cannot do that. But suppose you have it on the top of the trough and you give it a little nudge, it will roll down, then it won't be able to get back to that particular system, particular state. It cannot do that. So there is a natural direction for this particular system, but there is no way for it to come back to the way it was before. So this was what I was telling you. At the bottom or pinnacle, we have equilibrium states, but one of these is stable versus the other state. So in the first case, if you give it a small displacement, it will come back. In the second case, it will not come back to equilibrium. And these situations will have to be taken to real situations. So you can define that to calculate certain properties of the system. So for example, if the potential energy of the ball is equal to phi, how do you define the equilibrium stationary state? You define that by taking the zero derivative of the potential energy with respect to distance, or d phi by dr equal to 0. So from that you can calculate those values. Um, you also have to require that the potential energy be a minimum for the object, or phi is equal to a minimum. Okay, so that's all I have for this class. We will continue next Thursday. Thank you.